Yeah, hello everybody. I'm very sorry that I couldn't make it to Reno, but as you can see, I'm here and I'm in perfect shape. So we'll just need a little bit more time. When we met 25 years ago, I knew your work already, and I correlated success and age, and I was very surprised to see a man of my age, because I had thought you were much older, because you have done already those days so many nice things and pioneered so many investigations. So you were lively and determined as ever, and as soon as we sat down we had an intense discussion about delta 9 and delta 11 desaturases and so far and so forth. And actually I have never worked in this area, so I was more going for identification and synthesis of pheromones, and this was done in cooperation with many biologists. And today I'm talking about pollination syndrome, successful cheating, another way to survive. And this was done with Manfred Ayasse from the University of Ulm, Rod Pikal from Canberra, and Florian Schiessl from Zurich. These are the biological partners and who account for bioassays and for the material and so far and so forth. Now, the subject of the investigation is the Pouyan's mimicry. It has been described already 90 years ago, very carefully. Some flowers mimic the females of their pollinator by various clues. Optical, acoustic, and tactile phenomena are involved. They are cheating and attract the poor males of the pollinators to pollinate them. And it is said that one orchid species has one pollinator species, with some exceptions. I will come to this a little bit later. So here you can see one of those guys hugging and loving a flower, beautiful flower, and you can see in his eyes how excited he is and all wonderful situation. And in this case you can see here this all plant part, this organ, there are the pollinia hidden, and when he tries to copulate with his flower, the pollinia are glued on his head, and he leaves the flower with the pollinia glued on his head or on other body parts. We will see this a little bit later. Here it just happened. So this is the head of the bee. Two bees are competing for this flower, and here you can see the pollinia glued on the head of one of those guys. So what about the chemistry? There's of course color, odor, texture, and in this area we have been active, going for the scent that attracts. And the first pair is Ophrys sphygordis and Andrena nigroenea, and from the chemical point of view it was extremely disappointing what we found. Here you can see the experimental setup. This is the Electroantenography, which also has been pioneered largely by Wendell, and this is a very nice use of this system. It's very tiny antenna, but works very well. Manfred Ayasse did these experiments, and what we saw was a bunch of compounds, hydrocarbons, 23, 25, 27, and 29, and some unsaturated compounds, a bunch of compounds, eluting almost at the same time here. And they are all active on the antenna, and you can see that the cuticle extract of nigroenea with these very common lipids, almost all insects contain these compounds, and the labellum extract of Ophrys sphygordis coincide in these areas. And it seems to be the pattern, the mixture of these various compounds in the qualitative and quantitative correct composition to release the pheromone of the phenomenon of pseudocopulation. And here you can see how this works. Yellow is Andrena and red is Ophrys. And from C21 to C29, it's almost perfect coincidence, perfect match. So this is a pattern like an accord on a piano that needs to be together for maximum biological activity. Here are the compounds listed. So this is it, what I was talking about. After termination of fertilization, farnesyl is present in the bees and farnesyl hexanoate. The mechanisms how this is turned on is unknown yet. And the same compounds are also occurring in orchids, and their relative increase is strong after pollination. So what about other systems or similar systems? As I said earlier, one species of orchid, one pollinator. Here we have two non-sympatric species and having the same pollinator. And of course, they are attracted here and there, and they pollinate with their head. Here we have two sympatric species, and of course, the insect cannot afford to pollinate with the same body parts. So one is pollinated by head and the other is pollinated by abdomen. And the question is now, what about the chemistry that is involved in this case? Here you can see Nigroenea with the head, and here with the abdomen. And this is the chemistry that is involved. You can again see the backbone of saturated hydrocarbons, 23, 25, 27. And in addition, a bunch of unsaturated C25, unsaturated C27, and unsaturated C29 compounds. And it's rather complex mixtures that is represented in this case. 7, 8 unsaturated compounds of the same chain length. There's a lot of information in such a signal. In addition, you can see some qualitative differences here. In the earlier part there are of Ophrys hera, there are some compounds that are more volatile, but with one or two exceptions, they are not perceived by the antenna. Here is also a qualitative difference. These 60, 61, and also 59, they are Vox-type esters. We don't know whether they play an essential role, but we'll keep an eye on them. And if we think in terms of general patterns, this is the way. These are the wax-type esters that are specifically occurring in Ophrys herae. There are also some aldehydes, lower boiling aldehydes. Some of them may be active, we don't know yet. And then we have these typical saturated hydrocarbons and the corresponding alkenes as a bunch of rather complex mixtures. In addition, there are some dienes. You can see we do not know, we know the positions, but we do not yet know the geometry of the double bonds. So this is some work that's ongoing, and we have a lot of things to do still to get to the end of this story. Now the next pair is this classical Ophrys speculum Campsoscolia ciliata type, and here you can see this wonderful Ophrys speculum with this blue labium and wonderful shape, orchid-like and bee-like with these hairs around. Then you can see here the labium, and here you can see the blue shiny wings of the queen, and here you can see the fur, kind of fur, and similar also on the orchid side. Here in nature, two bees approaching, two males approaching Ophrys speculum, and here the great moment tries to copulate with the orchid, and here the pollinia are waiting for his head, and bang, he got it on his head. So here you see it. Now what about the chemistry? Again, we find bunches of hydrocarbons, very complex, saturated 29, 27, 25, 23, and complex mixtures of alkenes. The males also can do this a little bit, but it's qualitatively not as complex, and also the amounts are less. Comparing this with Ophrys speculum, one can see the Ophrys can produce even more compounds, and the unsaturated and saturated hydrocarbons are similarly complex in their compositions, and they are also dienes. So far, so good. So there are options. However, in this system, the hydrocarbons are not perceived by the male antenna. So this is kind of redundant system, though it is very flexible, like the other system that I just discussed about Nicoenea. It is not used. So we thought about more volatile compounds. And again, it was to our surprise, this is a volatile region, and one can see terpenes that is expected from the orchids, and to our surprise, it was also present a typical bark beetle pheromone. This is endobrevicomen. However, also these compounds are not perceived. They are there. There are options, but not used. What is used can be seen here. This is the red one is the EAG trace, and the white one is the GC. And there are some compounds that are active, EAG active, but the most decisive one is 9-oxodecanoic acid and the corresponding hydroxy acid here. And both in the labellum of Ophrys and in Campsoscolia, we find the same compounds. And with respect to relative concentrations, you can see how dramatic the situation is. This is the bunch of hydrocarbons that I just showed you. And this is the biologically active compound. This is a magnification of this area. Here, it's seen here. And it's these three compounds here. 9-oxodecanoic acid, just normal fatty acid, C12, and 9-hydroxy. And you can see this is a chiral compound, so we were thinking about the enantiomeric composition, and it turned out that it's neither a racemate nor a pure enantiomer. Here we have it, the 9-oxodecanoic acid and the 2-hydroxy acids. And if we compare, are there other compounds in the close chemistry or biology vicinity, then we came up with the queen substance of the honeybees. It's the same structure, same carbon skeleton. It's the same basic principle, because the hydroxy acid that occurs in the bees is also not pure enantiomers and also not a racemate, but shows a distinct enantiomeric composition. The only difference is the double bond here. This is it. And it shows that these two systems are very, very closely related, and points to evolutionary processes and evolutionary roots between these two systems. And here, once again, I have compiled the different compounds that are that play a major role. These are the decisive ones. The acid that is two carbon atoms shorter is also present, but it's not very active, and so are the other ones, though they may play an additional role. And finally, after pollination, these compounds decrease in their composition. Now, the third example is entirely different from the earlier ones. The first one was this very flexible compounds pattern that played a decisive role in pollination. And the third one, the second one was a one that resembled other systems that we know already from other Hymenoptera. 3 compounds is just fine. But in this case, Cheiloglottis trapeciformis and Neosiliboria cryptoides, here you can see the 2. This is a tinid wasp. They have just 1 compound. They play roulette. It's either or. And it's a small amount. This is number 7 here. The flower even produces a little bit more than, quantitatively, more than the insects. So this is a strange compound with 2,5 substituted cyclohexane 1,3 dione. We had a literature search, and that was the first cyclohexane dione with this substitution pattern. And one starts to think about the biosynthesis. How do these guys produce these compounds? And after quite some soul searching, I came up with a suggestion. It might be that an activated 3-oxocarboxylic acid reacts with an alpha-beta unsaturated acid that is activated here. And in this case, we would go for a Claisen condensation here, as the chemists term this, and on the other hand, a Michael type addition of this position to this one. This would end up with this compound, this intermediate, which after saponification here and decarboxylation would easily yield the target compound. Now, as almost all fatty acids, maybe they are built up or degraded. They are running through 3 keto acids by beta oxidation, and as an intermediate also this type of compound is involved in the biosynthesis or biodegradation of fatty acids. And if this is true, then one would expect that other compounds, additional compounds like with other substituents here, 4 carbon atoms here, or 1 carbon atom here, and 5 carbon atoms whatsoever, should also occur in nature. And that would mean we would have come up with this compound as the first member of a new class of natural products. So that we thought it might be worthwhile to study the mass spectrometry of these compounds that would give hints in the identification of new compounds in other systems. And here you can see the mass spectrum of this compound that we called Cheiloglotton. It shows a very distinct pattern, fragmentation pattern, and we investigated this fragmentation pattern by modern methods of mass spectrometry and used reference compounds, synthetic reference compounds, and so far and so forth. We came up with this type of chicken wire fragmentation suggestion, so to speak. I will not go into this too many details, but just depending on the substituent here and here, we will find, if this is true what we found, we will find mass spectra with distinct key fragments, and we could extrapolate and look for such compounds. Of course, prerequisite is to have a nice synthesis, so very easily one can do what I just described, in what may be the reason for the biosynthesis. One can, of course, also mimic this in the lab. And so we synthesized several analogs of Cheiloglotton. And there's another way. Meanwhile, there are other possibilities to produce these compounds. But you can also see here, if this residue is hydrogen, then we end up with no substituents in position 2, and we can insert this by simple calculation. And this would then be the biosynthesis, as I just pointed out earlier. And finally, we had success. It was just fine, because we could find some additional compounds. This is the chylogluttone in the first system. This is 2 carbon atoms longer at position 5. The same compound appears here together with this, so it's not 100% roulette, but 2 compounds just. And we found a third one with 1 carbon atom in position 5 and 4 in position 4. So this is ongoing work, and next time we meet, I will talk a little bit more about further results that we have. You can see everything is in progress, and I'm very much looking forward, Wendell, to meet you at another occasion, but now this is it. And I thank you for your attention, and I'm sure, Wendell, you will answer all questions that are now coming. Thank you very much.